Okay, class, so this is section 4.1, related rates from our OpenStax calculus book. And today we are talking about related rates, so let's introduce it. So related rates is the idea of, related rates. So we have many things in the world that are related in terms of relationships or functions, and as their rates grow, so do other rates or decrease. So let's talk about an example that I used in class. So for instance, let's say we have an oil spill. An oil spill that is out in the Gulf, kind of like BP's oil spill, right? Assuming that there is no current, no wind and stuff, this oil spill that was spewing out of the ground at the time would expand onto the surface of the ocean in a circular shape. So let's get a circle. Oops. Here's a circle. Beautiful. There's my circle. So, right, this is my circle. And let's assume also uniform thickness. So, uniform thickness. Just for simplicity's sake. So, uniform thickness. Let's say it's about 2 inches. So 2 inches also, which we could write as feet in terms of like 2 over 12, right, feet, which would be 1/6 of a foot. Okay. So with our uniform thickness and the fact that this is coming up as a circle, right, we can find the area of the circle, multiply by the thickness, and we'll have the volume. Nonetheless, so let's talk about this before. So now we got the volume. One thing about the volume we need to know, right? We can find the volume, yes. But one thing we need to know about it is that the volume is changing. It's still coming out. It's still spewing out of that well that's down there, and the oil is spreading out. And ever more the volume is changing, but also the radius is changing. So with respect to time, as the volume increases, as more and more oil comes up, this radius will expand. This radius will go forward, right? So what we are talking about are two rates. We're talking about one that we might be able to find out, which is dr dt, right? And the other one, which we want to find out, which is dv dt. This would be the ultimate goal of the scientists that are dealing with this oil spill, to try and figure out exactly how much volume is coming out. So we want to find, right, our dv dt. But let's say we can go out there on the boat and say, dr dt, I can figure out what the rate of change of my radius is by taking a boat out there and actually measuring how much the radius is changing. So let's, for simplicity's sake, let's say that's 5 feet per minute. Okay, so we have a radius changing at 5 feet per minute. And let's say we have a solid radius. So I want a radius, and we measured the radius and the diameter and found out that the radius was 300 feet across. And we want to figure out what the volume, what the rate of change of the volume is. Okay, so we're going to do that by relating these two. I'm talking about this and this. We're going to relate these two rates, hence the phrase related rates. We're going to relate them in terms of their actual variables, because R is a variable, and V is a variable. So let's find a formula to relate V and R. Our volume formula for this circle, right? For this, actually a cylinder, not a circle, because it is a cylinder with a thickness of, 1/6 of a foot. So what we do is we take the area of the circle, so that would be pi r squared, and we're going to multiply it by the height, which we know to be a constant thickness of 1/6 in this case. That is not a variable. That is not changing. So, but r is changing with respect to time, and v is changing with respect to time. So, going with that, let's go ahead and think about what else we got. So, all right, well, I'm trying to relate the rates, and I have a formula, right, with my v equals pi r squared times 1/6, right? But I'm trying to relate the rates. So one thing I could possibly do, because I don't have any rates here, is take the derivative. So now I'm taking the derivative with respect to time. Respect to time t, right? And this is typically the case with related rates. So I'm going to take the derivative of my formula here. I'll get for our v, we're going to take it with respect to time. So thinking of v as a function of time, I don't know what the function is. If I take the derivative of v, I get dv dt. Right? If I take the derivative, let me move things around. I'm going to say that's pi over 6, right? Just a constant being multiplied by r squared. If I take the derivative of r squared, I get 2 times r times, right? Because r is a function of time. I don't know what that function is, but we got to use the chain rule to say we're going to multiply by dr dt. So here is my derivative, dv dt. Right? And I want to be able to think about what we have here. So I guess I can simplify a little bit. So let me simplify a little bit. Let me say, okay, 2, right? I can cross off the 2, right? Make this a 3 kind of thing, simplifying just a teeny tiny bit before I plug in stuff. So, okay, so I am looking for dv dt. So I do know my r, we talked about it before, my r is 300, so I can replace at this particular moment in time, now that I've taken the derivative, I can replace the things that I know that are variables, but I now want to consider what they are at this particular moment of time. R is 300 and dv dt is, we were saying we measured it and it was 5 feet per second per minute. So we're going to multiply by 5 there. So things will again cancel. So we'll get, right, 300, that's 100 times 500. So we get a whopping 500 pi. 500 pi. What are my units on? So this is dv dt. What are my units on dv dt? Well, it's a volume with respect to time. And we can look over our actual units here and kind of see what's going to happen. But we get volume, right, in feet. So that would be feet cubed per our time, which is in minutes. And there is our answer for how much volume is coming out right at this particular moment, which would help our scientists to figure that out, kind of thing. So we could use related rates in this way, right? So I hope this was a good example in order to help us see how we can use related rates in general in life. So let's move on to some more, well, not so real world problems, but I think a set of problems that will actually help us figure out how to work related rates. So not so realistic, but we have a snowball is melting at a rate of 2, whatever. And if it remains spherical as it melts, at what rate is the radius changing when the radius of the snowball is 2 inches? So I think this 2, I think something happened in my copying of stuff. So I think this 2 is supposed to be 2 inches cubed per per minute. I forget if it's per minute or per second, but something happened in copying my Word document over. So, all right, we have a snowball melting at a rate of 2. If it remains spherical, sorry, it was 2. Wait, it was actually, sorry, I just noticed. I looked at my stuff here. So, and I noticed that this, what we're talking about, was actually in 2, it was supposed to be 2 feet cubed per hour. I'm just looking at my notes. I realized I have my notes right next to me. Okay. Excuse me. So a snowball is melting at a rate of 2 feet cubed per hour. If it remains spherical as it melts, of course, all snowballs remain spherical. No, just a joke, right? Snowballs do not remain spherical. Something just happened. My program coming back. Okay. So snowballs do not remain spherical as they melt, but, right, there's a ball, right? I have a radius of this ball. This is a horrible drawing, I know that, but I'm not really good with my iPad pen. I have a radius of that ball, which they're saying is 20 inches, but I don't want to plug that in because as the snowball melts, R is a variable. R is moving. R is technically decreasing, right? Is getting smaller and smaller along with the volume. So, which is what this is saying. So here's the steps. Okay, so we got steps we need to do for related rates. First, we're going to look for, so we're going to find out what we're looking for in terms of the rate. I want to figure out what rate I am looking for. And if I read over my notes, it says, what rate is the radius changing? Right? What rate is the radius changing? So that would say I am looking for dr dt in this case. I'm looking for dr dt. That's the particular rate. That's all I care about, right? And what rate, the second step is to find what rate is given. So what rate is given? Well, I'm given a rate up here, so, right, the one that I had to write in, which is actually a change in volume, because I have feet cubed, which is a volume per hour. So we have a dV dt. Excuse me. So we're given a dV dt of 2 feet cubed per hour. I don't like writing 2 feet cubed per hour right next to that because it confuses students. That is another step. Okay, but volume is changing with respect to time. It is shrinking, right? Whereas the actual, and so is the radius. These are two variables which we need to relate in terms of a equation. Okay, so looking for tells us what rate we're looking for. Given tells us what rate we're given, and then with related rates, what we're going to do is we're going to find an equation in terms of V and R. So now I need to think about my problem and think about what relates these two equations. So what relate these two variables in terms of an equation? So what we can find is that we have a volume formula. So we have a volume formula of a sphere, which is volume equals 4/3. So I'm sorry, this is my third step, which is writing an equation in terms of V and R alone, because those are given and looking for. So we're going to write our equation. Our equation is volume equals 4/3 pi r cubed for a sphere. That's just a standard volume for a sphere. So now I have an equation in terms of V and R alone, right? Everything else is a constant. Now that I have that equation, we can then do the fourth step, which is, because we're in Calc 1, take the derivative, differentiate. I think that's spelled right. Okay, so I'm going to differentiate my equation with respect to, t. So when I take the derivative of v with respect to t, that's dv dt, right? That is what we are given. If I take the derivative of 4/3 pi r cubed, I will get 4/3 pi, and I do for r cubed, that would be 3 times r squared, times, because it is a chain rule, dr dt. Whenever I have a variable and I'm using the this idea of related rates, I will always end up with my related rates that one that I'm given and one that I am looking for. Okay. So now that I have that, I guess I can do a little bit of boop, boop, canceling there kind of thing. So let's cancel those, and now let's rewrite the equation. So v dv dt equals 4 pi r squared dr dt. So now I need the fifth step, which is the last step. We need the win, or what I like to call the moment of time. We are going to plug in everything that is occurring at the moment of time. At this particular moment of time, we know for a fact that dv dt is given to us. We know that it is 2 feet cubed per hour. We are given that. That was our given. We also know that the radius is 20 inches, so I guess I'll just plug in 20 inches into this. Wait a minute. There's a problem. So this is a problem. I can't do this 20 inches because this is inches and this thing over here is in feet cubed. So before I plug in stuff, I need them in the same units. I need to think of the same units. I can't do this. Need same units. So need same units. All right, and so we're going to do a little work here and get 20 inches into the same units. I could do 2 feet cubed, but then I have to take into account that it's cubed and the number gets really large. So let's do 20 inches. I'm going to convert it into feet. So that would be 12 inches per 1 foot per 1 foot. And my inches cancel and I'm left with feet. So what do I get? I get 20 over 12 or 10 or, actually 5 over 3 feet. All right, now we can plug this in. So, right, we got the moment of time. We're doing a little bit of extra math to make sure our units are matching up. Excuse me. And we'll get 5/3 feet squared times dr. Sorry, that's a dr dt. Okay. So now I can solve for dr dt as our last step of our moment of time step. So let's just do a little math magic here and say, okay, well that's 2 equals pi, dang it, come on, pen, pi, 4 pi, 25 over 9 dr dt. I'm solving for dr dt, so let me just do a little more math. That would be 100 pi over 9 equals dr dt, which equals 2, and then I do a little math magic on this, multiply by the reciprocal, right, and I'll get dr dt by itself. When I multiply by the reciprocal, I will get simplification going on, right, the 2 and the 100 will cancel, and I'll get 50 pi in the denominator. And my units on this thing would be, because it is an r, dr dt, that would be, right, feet, I turned r into feet, over time, which is in hours. So, hours, let's write that a little better. All right, so there's our second problem. Well, technically our first, I guess, of the unit. The other one was an introduction. All right, let's get to the next one. Another realistic problem. Yes, a child is standing still. Oh, yeah, okay. It's not realistic because a child can't stand still. That's why. All right. Anyway, so a child is standing still and flying a kite. The kite remains at an altitude of 30 feet above the child's heads while traveling parallel to the ground at a rate of 10 feet per second. When the kite is 50 feet away from the child, how fast is the kite string leaving the child's hand? So let's think about what we got. We got a child. I am a beautiful jar. All right, here we go. Oh, man. My iPad. Come on. All right, so the child is flying a kite that is 30 feet above the ground. Seriously? Sorry, my iPad's causing some problems here. All right, it is traveling parallel to the ground, so it is 30 feet above the ground. All right, 30 feet above the ground, and it is traveling parallel to the ground, parallel to the ground, parallel to the ground. Okay. So with that in mind, right, it's traveling parallel to the ground, and so it is traveling parallel to the ground, and it is traveling in this direction, right, and they're giving us a rate of 10 feet per second. So, right, so this traveling distance that we're talking about here is varying. It is increasing as we go, as we let out string. So we don't know what it is, even though they give us this 50 feet away thing here. They give us that is increasing. So, and by the way, this 50 feet away from the child is technically the distance of the string. So we know that, but that also is coming out. That is a variable as well. As the child lets more and more string out of their hand, it will increase, making the triangle bigger and bigger and bigger and longer and longer and longer. And the same thing will happen on the top. Both of these are variables. We can call them whatever we want to, right? X and Y. Why not? Right? So let's look at what we got here. We got a rate that's given to us here of 10 feet, right, per second squared, right, and I need to figure out what that is. So I got my equation. This is a right triangle, by the way. We're assuming that it is traveling parallel to the ground, and the ground is perpendicular to us. So, okay. So, with that in mind, let's do our math. Let's do our related rates. What are we looking for? What rate in particular are we looking for? We are looking for when the kite is 50 feet away, how fast is the kite string leaving the child's hand? So we're looking for the rate of change of this side as it increases. So we are looking for the rate is dy dt. We are given that 10 feet per second squared. There's my rate. I understand that it's a rate because of the units involved as feet per second squared, right? And that 10 feet per second squared thing tells us what the rate is, right? And we're traveling parallel to the ground at a rate of this. So this is my dx dt. We are given dx dt. So I now need to relate my two rates, y and x. I need to find an equation in terms of y and x alone. So, I don't know where this stuff's coming from. We'll get rid of that stuff. Okay. So, with that in mind, let's get an equation going. So, equation in terms of x and y. So we are talking about a right triangle there. So there's a right triangle, and I can relate x and y in terms of Pythagorean's theorem. So we got x squared plus, right, the two legs squared. So Pythagorean's theorem, that is a 30. 30 squared equals y squared. Come on. Oh, my pen died. Y squared. Okay. Excuse me. So now I have an equation of terms of x and y alone. That's the idea of the equation step. So after that, we can do our fourth step, which is differentiate. We're going to differentiate with respect to t. So when I take that derivative, I get 2x times dx dt. Every time we take the derivative with a variable involved, we will get a dx dt or a d whatever dt kind of thing. So, and if I take the derivative of 30 squared, whatever that is, that's 900, or 900, and that is 0. So if I take the derivative of that, that's 0, and then this equals 2y times dy dt. So I need to have both dy dt and dx dt for this to work, because we're given dx dt and we're looking for dy dt. So now we have, right, to kind of simplify this, we can cancel out the 2's if we want to by dividing by 2, right, and then we got the moment of time. So in this moment, now we're going to plug in what we're given. We are given, are we given x? I'm looking at this going, oh, where's the x? Where's my x? No, I don't have x. I need to find x, right? I am given dx dt, which is 10, right? I need to find x. So we need to find x, so I'm going to leave a space in there. Y is, they give us y. They give us y as 50 feet, right? At that particular moment, y is 50, and we are looking for dy dt, right? So I can't solve this as is right now because I need to find x. I need to find x. So how the heck will I find x? Well, we're going to use our formula. We're going to use our equation. And this is typically how it goes. We're going to use our equation to find x. And how I know that x squared plus, right, 900, our original equation, equals, right, I know y. In this moment, y is 50. So, right, this is 2,500, right? And I'm going to subtract 900 from it, 2,500. We are going to subtract 900 from it, and we'll get x squared equals, what will we get? That would be, 16, isn't it 1600? Oh, if I take the square root of that, right, I get 40. Right, plus or minus 40, but we are talking about a distance, so we're not worried about it. We're talking about 40 feet, technically, for x. Using Pythagorean's theorem. Now I can come back to my original equation and plug in my 40 for my x. All right, so now that we got the equation, we can solve for y just by dividing by 50. Right, if I divide by 50, then I'll get dy dt equals 40 times 10 is 400, divided by 50, I believe, is 8. We're talking y is in terms, dy is in terms of feet, dt is in terms of seconds. So 8 feet per second. Okay, so with that in mind, we are done. And I'm realizing now that I messed up on the last one. I looked at my notes for a second, so let me take a step and go back from my last one. I really messed up here. I really messed up big time. Why did I mess up big time? Because my feet squared, 2 feet cubed per hour, is melting. We are melting, so we're talking about an actual negative thing, so which changes my solution. Oh man, I messed this thing all up like this, which changes, right, this to negative. So as I change the rest of it to negative, all of it becomes negative, as it should be. Man, I can't believe I did that. There we go. Fix it, Andre. Good job. I don't have my students helping me in class. That helped me. So, all right. So with that in mind, let's go on to the next one, the third one. Right? So very similar to actually the first one. So it's a good thing I went back to that first one to remind us of what we did in the similarities. Yeah, that's what I was doing. Right? Do you buy that? Okay, no. All right, moving on. So, okay. So we got an ice cube melting. Instead of a sphere melting, right? Instead of a snowball melting and staying as a sphere, we got an ice cube melting, right? Very different problems. Just kidding. But it did work out to be different in terms of how we work the related rates. So let's see what happens. So when the volume of the cube is 8, so 8, we are talking, again, my stuff died on me here, we are talking 8 centimeters cubed. The volume, when the volume of the cube is 8 centimeters cubed. Okay, my notes kind of died on me. My word died on me when I transferred it over. It is melting at a melting rate. Okay, so this is bad English. It is melting at a rate of 4. At a rate of, sorry, melting at, get rid of that one. Melting at a rate of 4, what do we got? We got 4 centimeters cubed per second. Melting at a rate of 4 centimeter cubed. So I don't want to mess up again, right? I don't want to mess up again. So let's notice, right, what this is. We are really talking about a negative, right, because it is melting 4 centimeters cubed per second. Okay. So find the rate of change of the surface area of the moment. So we are talking about a cube. So let me draw. Woo, what happened there? I didn't even know I could do that. Cool. I don't know why that one didn't work like that. Me neither. I don't know. I don't know what's happening. I'm still trying to figure out my iPad here. So sometimes it gives me a straight line. Sometimes it is. That's a pretty good cube though, right? So, alright. So, alright, I can have some dashed lines here, right, to kind of establish the cube. There we go. Alright, there's my cube, right? And so the volume of a cube, right? So if I particularly, no, I don't want to do that yet. So let's think about, right, what we're doing here. There's my cube. I am looking for, right? So let's describe what we're looking for. Let's do it. Let's do the problem. Looking for. What are we looking for? Rate-wise. Find the rate of change of the surface area. So we are looking for the rate of change of a surface area. So let's say dA, I can do dA dt. dA dt. We're looking for dA dt. What rate are we given? So looking at the notes, right, I have the rate we're given is that negative 4 centimeters per second, centimeters cubed per second, which is a dV dt. All right. So given dV dt. So now that we know all that, right, I need to relate my two variables here, only my two variables, only these two variables. I need to find an equation to relate my volume to my surface area. So my volume to my surface area. That is a little strange, so let's go back and think about volume and surface area. So if I want to think about volume of this cube, right, a cube has all the same sides, so I can call that x, that is an x, that is an x, and that is an x, right? So if I want to find volume, right, we're thinking about the equation piece, that would be x cubed, right? Right? If I want to find surface area, so surface area, which would be, if I look at the sides, right, I have one side here, which, right, has an area of x squared. So, but I have how many sides? I have 1, 2, 3, 4, and a top and bottom, 5, 6 sides. I have 6 times x squared. So as my area, that's my surface area of this cube. So I want an equation. So my next step is that I'm trying to do here is finding an equation, but we want that equation only in terms of V and A, because those are what we're looking for and what we're given, right? So what we can do is we can solve one of these equations for x, right? And I don't like square rooting. That's just me, right? Square rooting causes issues. We usually have to do plus and minus thing. In this case, we could get rid of the minus because we are talking about area, right? And a length. X is a distance. So, but anyways, to make it straight, what we do is we can actually just take v equaling x cubed, and we can take the cubed root of it. Right, take the cube root of it. Cube root works a lot easier than square root because, right, we have no issues with cube root. So this would give us that x equals the cube root of v. Okay, well, so we got one thing. We got x's. What we can now do is we can now substitute in x for that x up there and say that the area then equals 6 times the cubed root of v all squared, because x is being squared. So simplifying this a little bit, right, I get a equaling 6 times v to the 2/3 power. Okay, we're getting there. So now talking about taking the derivative with respect to t. So I'm going to take the derivative of a with respect to t is dA dt. I'm going to take the derivative of this other side and say I get 6 times 2/3 v, subtract 1 for the power, so that would be negative 1/3 power, times using chain rule. Don't forget the chain rule. And right, v is a variable that we're taking the derivative with respect to time, so chain rule applies. So with this implicit differentiation I do. So I can see some canceling going on. So let me cancel 2. Make things a little simpler for myself. I'll get dA dt as, I guess I'll get 4 over the cubed root of v. Right? The cubed root of v times dv dt. So now I need to go back and think about what I have and what I'm looking for. I was looking for dA dt. I am given dV dt, which was a negative 4 centimeters cubed per second. We are we given the volume? Yes, we are given the volume at 8. So I have everything I need. dA dt is equal to v 4 over the cubed root of 8 centimeters cubed, and dV dt is negative 4. I didn't forget the negative this time. What happened there? I did not forget the negative. All right. So what do we have? We have, simplifying this, the cubed root of 8 is 2. 4 divided by 2 is 2. Negative 4 times 2 is negative 8 again. So negative 8. We are talking about area over time. So this is, we had centimeters squared is the area over time, which is in seconds, as our units. Don't forget the units. The units are huge in this case. We want to think about those units, right? And again, you can think about what is going on with the canceling of units to determine what happened to the units. And it's a super cool way to think about differentiation. Okay, so moving on. All right, next problem. Stepping it up a notch. So we've seen that, right? We have some easier relations, right? Coming up those equations a little bit hard sometimes, right? Being able to talk about how to write it in terms of V and A alone, in that case, in that previous case. But now we need some trig involved. So, okay. So let's talk about this one. So I have a rectangular sign. 24 feet wide, of negligible thickness, turns at a rate of 5 revolutions per minute, about a vertical axis through its center. A distant observer sees the sign as a rectangular of variable width. How fast is the apparent width changing when the sign is 12 feet wide as viewed by the observer and is increasing in width? All right. So this one is tough to actually see what is happening, but I have a rectangular sign. So there's my rectangular sign spinning, right? Spinning. It's supposed to be an arrow. There we go. I have a rectangular sign spinning, right? It is 24 feet in width here. So I know that's kind of a length, but whatever. You get the idea, right? Here's my sign. Okay. All right, so my rectangular sign is that. So, and it is spinning, but we are actually viewing this thing. We are trying to think of the apparent width. So as, right, we spin this thing around, things, the width here, so this width will get smaller and smaller and smaller. All right, making it smaller and smaller and smaller. Whoops, I got rid of stuff I didn't want to get rid of. So making it smaller and smaller and smaller. What I'm saying is, so thinking of a top view, if I have, right, my rectangle, wow. So there's my rectangular sign from a top view with the center, that's my pole that's sticking through it. So this distance here is 24 feet, right? As it spins around, we are going to get a nice circle. So beautiful. My drawing's so beautiful. As it spins around, right, it's going to make a nice circle from the top view. Kind of thing. So, all right. Excuse me. Okay, so with that in mind, what we have and what we're talking about is we are trying to figure out how fast the apparent width is changing. So if I am viewing this thing, and here's me, kind of a top view of me, right? There's my eyes. I am facing this thing and looking out this way. So boop, boop, I'm looking out this way. So as we go. So I'm looking this way. This is me. Here's my hair. Whee! Right, I'm a little bald. Okay. Anywho, so this is me. All right. Three-dimensional body there. I look completely upside down. This is horrible. Okay. Hopefully you get the gist. I'm over here looking at my sign, right? And when I look at my sign, this distance here, let me go back. I want a different color. So let's use colors. This distance here is the apparent width for me. This distance here is my apparent width. Not the 24. Not the 24, right? I don't see 24 feet. I see whatever this is, kind of thing. So hopefully that makes sense of what we're doing, right? Play around with a thing. This kind of comes up, this idea comes up in a computer graphics. So let's think about this. All right. So let's think about this. So what can we do? So what we really have here is a triangle. So here's my triangle. It is a right triangle with my apparent width over here and a solid 24 on this side. As we spin around, we are going to spin around right in the middle. As we spin around, we get an angle, right? As we spin around, and it's going to get in bigger, so I'm going to spin it this way, which is the correct way of it. So that is the correct way to do it. So my angle is changing. So how do I want to do this? So this angle that I'm trying to draw in this corner is the same as this angle. So as I spin around, right, we're thinking of that angle. So what do I have here to relate these two? So what I have is this side's 24, this side's W, and this angle is what we'll call theta. All right. So, all right, where am I going with this? I had to do all this setup so we can then talk about it. So what are we looking for? Rate-wise, looking for how fast the apparent width is changing. So that is my dW, dt. Just kidding. That's for you Arthur fans out there. All right, looking for dW, dt. We are given, what rate are we given? We are given that the sine turns at a rate of 5 revolutions per minute. So we are given how fast it is turning, how fast. We are given an angular speed. We are given d theta dt as 5 revolutions per minute. So let's take a step here. I want to take a step because hopefully you're as grossed out by this as I am. So hopefully you're as grossed out by this as I am. So revolutions per minute. It is a common, right, unit of angular velocity. But nonetheless, revolutions per minute are difficult to use. So angle-wise, do we like degrees? We do like degrees to think of degrees, but what do we like in our equations? We like radians. So I'm going to convert this to radians. In 1 revolution, there is 2 pi radians. So canceling out my 2 pi, so my revolutions, I will then convert this d theta dt into 10 pi radians per minute. Okay, that makes me happier. Okay, so, and we are at a positive angular speed there, and as I increase my angle, right, my stuff will increase as well. My sine will increase the way I've drawn this out, and that is important. If I drew this wrong, if I drew this angle backwards, so something like if I drew this angle going this way instead, then essentially what would happen is that we would get a negative case. So, and this is a good problem to think about in general, because sometimes we end up with the opposite of what we want. But the problem does state that we are looking for, right, a distant observer sees the sine as a rectangular variable width. How fast is the apparent width changing when the sine is 12 feet wide as viewed by the observer and is increasing in width? So we are increasing width. If I draw this blue, if I draw my angle, if I draw my angle as going clockwise, then we are rotating the wrong way, and my trigonometric functions won't work properly. All right. Okay, so let's go for it. So why am I talking about all this, right? So now I'm going to try and relate 2 variables. I am going to try and relate my given variable theta to my apparent width w. Those 2 alone. So we got to write the equation as the next part. We need an equation to relate those, right? 2 things. So I need to think of an equation that relates an angle to 2 sides, in particular an angle to my adjacent side and my hypotenuse. That would be a cosine function. Cosine of theta equals w over 24 would be an equation we can use. Where is my a for my equation? I don't know. Okay, so now what we do now? So now we do the moment. Now we do the moment of time. So we're going to plug... Oh, no, we don't. What am I talking about? We don't do the moment, Andre. Get rid of the moment. After the equation comes... I got to take the derivative first. I need to plug in stuff. I need to plug in stuff with d thetas and dw's, dt's. So, right, take the derivative with respect to t. So I get negative sine of theta times d theta dt. D d theta dt. Right, this is why we need radians, because this d theta dt, this angular velocity, is outside the sine function, and we cannot use anything else besides radians when we're outside the sine function. Okay, so then w, take the derivative of that. That would be 1 over 24 times dw dt, dwtt. All right, so what do I have? So I now need my moment. This is the appropriate time to do the moment. After I differentiate, I'm going to plug in what I have, knowing that I have sine of theta. Sine of theta. I don't know what theta is. Darn it. I'm having problems here. I just realized I'm having issues because I don't know what theta is. Huh. I wonder what I do. I do know what d theta dt is. D theta dt we just talked about was 10 pi, right? I need to figure out what negative sine theta is. So I'm not sure how to do that. I got 1 over 24, and I'm trying to find dw dt. I'm trying to find dw dt. Right? So I need to find something to help me figure out what negative sine of theta is. So what do we have? Well, I have my triangle. So I have my triangle, and the fact that this moment in time, we know that we have 12 as the apparent width. We want to change the apparent width. So we have a triangle now. We have a triangle that looks like this, with 24 here and 12 here, and my theta here. This is my triangle. So with that in mind, I can say that cosine of theta equals 12 over 24, which equals 1/2 at this particular moment in time, right? But theta is changing. But at this particular moment in time, right, when is cosine of theta equaling 1/2? It is on the unit circle, which actually happens at pi over 3, sorry. So theta is pi over 3. Theta is equal to pi over 3, which allows me to say that I'm going to come up over here now, negative sine of theta, pi over 3. Oops. Let's get rid of theta and put pi over 3. Would be negative root 3 over 2. All right, so we got negative pi over 3. We can come back and plug that into our equation up here and say, oh, I got negative root 3 over 2. So let me copy this equation, right? And I'll paste it down here, I think. How do I do that? Copy, paste. There we go. All right, we're almost there. Move. No, that didn't work. Okay, anywho. So I'm just going to finish it up here. So let's see what we got. So I'm going to multiply by 24 and solve this. So I can see my 2 canceling. My 2 canceling with my 10, I get 5 pi. And then we're going to multiply by 24. 24 times 5 is 120. I get 120. So in particular, though, because I have a negative out there. I'm seeing something happen. I got a negative 120 root 3. I'll go backwards. 120 pi times root 3 equals dw dt. That is a dt. Okay, that is my answer right now. For right now, but I have a problem. So I'm noticing that my dw dt is negative when it was supposed to be actually increasing. So my apparent width was supposed to be increasing. So what do? Well, I noticed that and I say, well, something happened to my mathematics, and I can go back and fix it. My pen died on me again. There we go. Right, so I can go back and fix it, but this is going to be positive. That's really all that's going to happen here. So let me go back and think about what happened with my work involved here. So as I increase, I'm not sure. I thought I set it up correctly to be able to do this so that my angle would come out positive, and I'd even talked about it up top here, where I was turning the right way to make it increase. No, what's happening? Yeah, going back to the top. My angle, I did mess this up because my angle is technically decreasing, right? As we make it smaller, we're going to make that smaller and smaller, that angle. So it's just, what's happening is my theta is actually negative. So I should have my theta being negative. Right. Or actually, no, not my theta. Sorry, my d theta dt. My d theta dt should be negative, because that's what's changing. My d theta dt is getting smaller and smaller, technically, in this way I drew this. So that would change my equation and make this negative as I multiply it, which would change my equation down here to be negative, right? Which makes it all positive. So as we said, all right. So sorry about that. Here we go. So now we can move. Oh, wait. I didn't talk about the units here. What is the units on this thing we're talking about? So we are talking about dw dt. dw is the width, right? We are talking about feet per minute. Ay, caramba. Feet per minute. All right. So let's move on to the next one. All right, next one's a good one. So we got to consider a rubber washer that is being compressed. At a certain time, the following measurements are obtained. The outer diameter of the washer is found to be 3 centimeters. The inner diameter of the washer is 1 centimeter. The thickness of the washer is decreasing at a rate of 1/4 centimeter, 1 centimeter per minute. The outer diameter is increasing at a rate of 1/2 centimeter per minute. If the volume of the washer remains at all times pi, it's supposed to say, if the volume of the washer remains at all times, so again, something's happening to my notes when I transferred my Word document over to there. Pi, right, we're talking about centimeters cubed, I believe. Looking at my notes, centimeters cubed is the thing. So here we're talking about pi centimeters cubed is the volume. At what rate is the inner diameter changing at the time in measurements, the time the measurements are made? So, okay, so kind of a long problem. All right, but let's think about it. So, all right, so we have a washer. Right? So just a quarter with a hole in the middle. We have an outer diameter. We have an inner diameter and an outer diameter. So my inner diameter. So D. So let's use, because I can't write too well with these, let's use A and B for diameters, okay? I'm going to have problems writing a little subscript notation. So I got my inner diameter here. So dang it. Problems using my iPad again. Here we go. Inner diameter. So, no, still problems. Still problems. I just want to use some colors. So let's call this this inner diameter B, and my outer diameter A. Just to make the notation a little easier, because I'm having a hard time writing clearly with this thing. So outer diameter, and then there's a thickness, right? A thickness. So we're trying to find the volume. I got some thickness to this thing. So, right, I have my thickness. Which we need to call something. I don't know. Let's call it H. So, right? All these things, B, A, and H, are changing. They are variables with respect to time. As I squash this thing, H is getting smaller. As I squash this thing, B is getting smaller, right? My inner diameter is going to condense, and so is my height. But as I squash this thing, my A is actually going to get increase. So it is a rubber washer. It's going to move. Our volume is staying the same. So is what it's saying, as pi centimeters cubed. So this matter needs to go somewhere. All right, so let's do it. Hopefully we understand what I'm talking about. So here we go. We're looking for what rate? What rate am I looking for? The volume of the washer remains. At what rate is the inner diameter changing? What rate is the inner diameter? We're looking at the inner diameter. That is dB dt for my inner diameter. What rates are we given? Right, notice I use the word rates, because I am given a few rates here. I am given that the thickness of the washer is decreasing at a rate of 1/4 centimeter per minute. We are given dH dt. And I am also given that the outer diameter is increasing at a rate. We are given dA dt. I need to relate all three of these things with an equation. An equation. So our next step is finding the equation to relate all three of those variables. All three of my H, my A, and my B. Okay. So I need an equation to relate those, and we are going to relate them in terms of our volume, because we're given a hint that volume is a constant, pi centimeters cubed. So we are going to relate it in terms of our volume. And volume, this is a cylinder. I do have two cylinders technically. I have one outer diameter cylinder, and then I need to take away the inner diameter cylinder because we are missing that bit. So we're going to use a volume of a cylinder. So think about the first problem. We talked about the area of the oil spill. So volume of a cylinder would be pi r squared h. Right? So I need pi r squared h. So my volume, right, for my outer, right, I will take pi r, right? R will be, I take my diameter, divide by 2 to get my r, and I'm going to square it. Then I'm going to multiply by my h, my thickness. We're going to multiply by my h, which is my thickness. So this is my outer diameter thickness, right? I'm going to subtract off the stuff that's missing inside. I'm going to subtract off the stuff that's missing inside. So that would be pi, right? Again, I'm looking for my volume there of my inside cylinder, which would be the inner radius, b over 2 squared times h. So there's my equation. I'm going to simplify this thing a little bit and notice that my pi, my volume, is a constant, right? Whereas my A, my B, and my H are changing, but my volume is pi. My volume is pi. I'm kind of simplifying things. I get pi over 4, right? Because my 2 on the bottom gets squared. A squared times H minus, again, pi over 4. B squared, or not, depends on what you want to do. So I am personally squared. All right, so So let's see. So what do we have here? So I'm looking at this. I want to simplify some more. I'm looking at this thing and I'm going to say, oh man, there are two product rules that I possibly have to use. Instead of doing a product rule, maybe I could multiply both sides just to simplify my life a little bit. You can use the product rule. It can work, right? But I'm noticing some other simplification. So I'm thinking about pi, h, and 4, right? Pi and h are on the top. What I can do is multiply by the reciprocal of all of that. So, right, things will cancel. Everything will go away. My h there, my pi there, my 4 there. When I distribute this, my h here, my pi there, my 4 there, right? And then when I multiply this on the other side, my pi's will cancel. So I'll get 4 h to the negative 1 power equals a squared minus b squared. Okay. So there's the relationship, there's the equation that I want to use. So now we do what? Right? Well, we're in Calc 1. The next step is differentiate with respect to t, so I'll take the derivative. Now you kind of see why I put it as negative 1 power. Using the power rule, I get negative 4 h to the negative 2 power times dh dt. Don't forget it. Don't forget, it's so easy to forget. 2a times dA dt. Don't forget it. Every single variable, we're going to have a dt thing. So, and then 2b, or not to be, times dB dt. Almost there, almost there. It is that moment in time now. So we are going to plug things in that we know. So looking back at the problem, what do I have? Hopefully I don't have to find everything. So what do we have at this moment in particular? We got d. So we got dB. Don't we have dB? What do we have? We're looking for the inner diameter and how fast the inner diameter is canceling. But we do have dH dt. dH dt equals negative 1/4. Right? Whereas, what else do we have? We had dA dt, which is my outer diameter, was changing at a rate, the outer diameter is increasing, so it's positive 1/2. We are also given that that A equals 3 at this moment, and my inner diameter, my B equals 1 at this moment. The other thing that I need, if I look, I need H. So how do I find H? Well, I use our original equation to find H. So I do have to plug it in, and solve for H. So the original equation being this equals A, which is 3 squared, minus B squared, which is 1 squared. So I'll get 8 here equals 4 over H. If I flip everything, right, and multiply by 4, I will get H is 1/2. 1/2 centimeters. So now I can plug everything into my equation. So now I can plug everything into my original equation, my differentiate equation, right? So I got negative 4. Negative 4 times H, right, to the negative 2 power. H to the negative 2 power. Times my dH dt. dH dt is negative 1/4. Equals 2 times A, which is 3. Times dA dt I have as 1/2. Minus 2b, or not to be. Sorry, I cannot say that without saying the joke. All right. dB dt is what we're looking for. So let's do this. All right. So over here, what do I have? This thing is flipped because of the negative exponent, and then squared. So I got 4 there. So that's negative 4 times 4 divided by negative 4, which would be positive 4. I get positive 4 for this whole side. Over here, the 2's cancel. Right? These 4's cancel as well. So positive 4, and so do the negatives. So then I get 3. Over here, I get, right, 2's cancel, and I'll get 3 minus 2 dB dt. Solving for dB dt, I subtract 3, I'll get 1 equals negative 2 dB dt. One more step, and I'm almost there. Oh, it's so close. I'm so excited. Dun, dun, dun. Booyah. All right. So this last one, this pool one, I am leaving for you to do as homework, right? The hints we need for this last one are, we need the area of the trapezoid, an area of the trapezoid, right? If I call this x and this y and the height y, the height as h, kind of thing, then my area of my trapezoid would equal x plus y over 2 times h, the average of the bases times h. Right, to get the volume then, right, they are giving us the swimming pool is 20 feet wide constantly. I would take my area of my trapezoid and times it by my width, which is 20. So just the solicitor. All right, had to check it. So let's see. So I need my volume, right? So we're going to find the volume like that. But so one thing to notice is that this pool, right, the top here is the top base. That is our y. It is increasing as I pour more water in that. Okay, and this shallow end doesn't really matter, right? These are the biggest hints I can give you. The next biggest hint is that we are going to get 2 sets of similar triangles here. Look at the smaller set. Here's a small triangle. Here's a big triangle. Those are similar, right? As well as over here. I'm going to need to write similar triangles in order to express these distances here in terms of h, in terms of our height. So, whereas this is just 12. All right. Biggest hints I can give you. All right. Go to town. Thanks.